Picture this, a silent, invisible force so immense it can warp the very path of light, twisting emptiness into brilliance and chaos into creation. This isn't science fiction, it's the story of magnetic fields and what happens when they spiral wildly out of control, giving birth to some of the most spectacular light shows in the cosmos. From the dancing curtains of the auroras that paint our polar skies to the violent eruptions on the surface of distant stars, these events are more than just beautiful, they're fundamental expressions of how our universe operates. And behind each one lies a thrilling tale of instability, transformation, and raw cosmic power. You've probably felt the pull of a simple magnet or used a compass pointing north, but that's just a whisper of what magnetic fields can do. In the depths of space, they shape galaxies, guide stars, and when pushed to their limits, they unleash energy that can outshine entire suns. We're going to explore exactly how these fields form, why they sometimes break into magnificent turmoil, and how that chaos culminates in the birth of light itself. It's a journey that will take us from the familiar glow of the northern lights to the heart of neutron stars and the explosive frontiers of gamma-ray bursts phenomena that challenge not only what we see, but how we understand reality. By the end of this video, you'll see the night sky differently. You'll understand why scientists are so captivated by magnetic mysteries and how these invisible forces touch everything from the technology we use every day to the farthest reaches of space. Whether you're an avid stargazer or simply curious about the hidden workings of the universe, this exploration promises to illuminate one of nature's most mesmerizing performances. So settle in, we're about to unravel how chaos gives rise to light, and why this dance of magnetic fields is one of the greatest stories the cosmos has to tell. Think about the last time you held two magnets and felt that push or pull between them. That invisible tug of war is a tiny glimpse into one of the universe's most fundamental forces. Magnetic fields are all around us, shaping reality on scales both intimate and cosmic. They're not made of anything you can touch or see. Instead, they're like intricate webs of influence, patterns of force that reach through space to guide and sometimes dominate everything they touch. At their heart, these fields come from motion specifically, the movement of electric charges. Every time an electron zips through a wire or a charged particle swirls within a star, it generates a magnetic field, weaving an invisible architecture of energy that can stretch across light years. Earth itself is a perfect example. Deep below our feet, our planet's molten core churns with currents of iron and nickel, a dynamic, swirling ocean of electrically conductive material. This motion doesn't just give us gravity, it acts like a colossal generator, producing the magnetic field that envelops our world. That field reaches far out into space, forming a protective bubble known as the magnetosphere. Without it, the solar wind, a constant stream of charged particles from the sun, would strip away our atmosphere and bathe the surface in harmful radiation. So in a very real sense, this magnetic shield doesn't just give us the beauty of the auroras, it helps make Earth a living world. But magnetic fields aren't unique to planets. They emerge wherever charged particles are in motion. Inside stars like our Sun, ferocious heat turns gas into plasma, a state of matter where electrons are torn from their atoms, creating a seething, electrically charged soup. The turbulence within forces this plasma to spiral and twist, amplifying magnetic fields to incredible strengths. In galaxies, magnetic fields thread through the vast clouds of gas and dust between the stars, influencing how those clouds collapse to form new solar systems, and sometimes even guiding the birth of stars themselves. What's fascinating is that magnetic fields are incredible storehouses of energy. When stable, they act like cosmic conductors, directing the flow of charged particles and shaping structures without much fanfare. But when conditions grow extreme under intense pressure, wild temperature swings, or in chaotic gravitational environments, these fields can be stretched, twisted, and compressed until they become unstable. Like a coiled spring held too tight, they hold onto immense energy until something gives way, leading to spectacular and often violent releases. That transition from order to chaos is where the magic happens, where magnetic fields spiral out of control and create light. But what does it take to push these powerful, structured fields over the edge into chaos? Stability is the norm, but the universe is filled with extreme environments that love to disrupt the status quo. Imagine a calm, flowing river suddenly hitting a steep waterfall. The water's smooth motion breaks into violent, chaotic turbulence. Magnetic fields behave in a strikingly similar way when they encounter intense pressure, drastic temperature shifts, or the powerful influence of other magnetic fields. These forces act like cosmic wrenches, twisting and contorting the invisible lines of force until they can no longer hold their organized shape. Think about the sun's surface, a seething cauldron of superheated plasma. Here, the constant churning motion stretches magnetic field lines like taut rubber bands, packing them with immense energy. When the tension becomes too great, something has to give. The fields can snap, tangle, and violently reorganize themselves in a process that is both destructive and creative. This isn't a gentle unraveling, it's a sudden, explosive transition from order to mayhem. In the crushing gravity near a black hole or within the furious atmospheres of distant stars, these instabilities don't just happen, they amplify, creating a feedback loop of magnetic chaos. This breakdown of orderly magnetic lines is often the precursor to one of the most important events in all of astrophysics, a magnetic reconnection. When field lines are forced together from opposite directions, they can cross, break, and then rapidly reconnect into new, lower energy configurations. It's a bit like cutting two stretched, tangled rubber bands and then instantly fusing the cut ends into new pairs. The energy that was stored in the stretched fields has to go somewhere, and it's released in an incredible burst of power. This single process is the engine behind solar flares that can disrupt communications on Earth and the breathtaking auroras that dance over our poles. These instabilities are the crucial turning point, the moment when stored magnetic energy is converted into other forms. They set the stage for the universe's most brilliant light shows, transforming silent, invisible forces into a spectacular symphony of radiation. The stage is now set for that very transformation, where chaos becomes creation and magnetic turmoil gives birth to light itself. Now, let's zoom in on that pivotal moment when magnetic chaos crystallizes into something extraordinary, the process known as magnetic reconnection. Picture two powerful rivers of magnetic force flowing toward each other from opposite directions. They're not just pushing against one another, they're being squeezed together by immense pressure, often in a superheated plasma where particles are zipping around at frantic speeds. At a critical point, the tension becomes unbearable. The magnetic field lines those invisible structures that normally repel or guide are forced to cross. It's a bit like two clenched fists suddenly slamming together, fingers interlacing in a violent, unexpected grip. In that instant, the fields snap. They break apart from their original configuration and then, almost instantaneously, realign into new, more stable patterns. This isn't a gentle rearrangement. It's a fundamental reorganization that unleashes a staggering amount of energy. Think of it like stretching a giant elastic band to its absolute limit until it tears, and then watching as the stored energy explodes outward. In magnetic reconnection, the energy that was once bound up in the twisted, stressed magnetic fields is rapidly converted. A huge portion transforms into kinetic energy, violently hurling particles away at a significant fraction of the speed of light. Another portion becomes intense thermal energy, superheating the surrounding plasma to temperatures of tens of millions of degrees in a matter of seconds. The sheer power of this process is almost incomprehensible. In a large solar flare, a single reconnection event can release energy equivalent to millions of 100-megaton hydrogen bombs detonating simultaneously. It's one of the most efficient energy conversion mechanisms in the entire universe, but its effects aren't just about raw power, they're also about precision. On Earth, this same process acts as a delicate trigger for the auroras. When the solar wind, a stream of charged particles from the sun, pushes against Earth's magnetic field, it can force reconnection events on the night side of our planet's magnetosphere. This acts like a slingshot, flinging electrons down along the magnetic field lines toward the polar regions. When those electrons smash into oxygen and nitrogen atoms in the upper atmosphere, they excite them, causing them to release that energy as the shimmering, dancing light of the northern and southern lights. The most fascinating outcome of all this mayhem is the creation of light itself. As those particles are accelerated to incredible speeds during reconnection, they don't just travel in straight lines. They spiral along the newly formed magnetic field lines, and this sudden, violent acceleration forces them to emit radiation across the entire electromagnetic spectrum. From radio waves to visible light and all the way up to high-energy X-rays and gamma rays, magnetic reconnection paints the cosmos in a full palette of light, transforming silent, invisible magnetic turmoil into a brilliant cosmic spectacle. So what happens to all those particles flung into chaos by magnetic reconnection? They don't just vanish, they become the universe's ultimate light bulbs. When magnetic fields spiral out of control, they act like nature's most powerful particle accelerators, far surpassing anything we can build on Earth. Charged particles, mainly electrons and protons, get caught in this turmoil and are whipped up to velocities approaching the speed of light. It's as if these particles were suddenly thrown onto a cosmic racetrack with impossibly high banks and curves, forcing them into a frenzied dance. But here's the crucial part. When you accelerate a charged particle, it must pay an energy toll, and that payment is made in the form of light. This light creation happens through several fascinating mechanisms, each with its own unique signature. One of the most common is called synchrotron radiation. Imagine an electron hurtling through space, caught in the grip of a powerful magnetic field. The field doesn't let it travel in a straight line. It forces the electron into a tight, spiraling, or curved path. This constant change in direction is a form of acceleration, and each time the electron is forced to bend its trajectory, it emits a photon, a particle of light. The tighter the spiral and the stronger the magnetic field, the more energetic the light that's produced. This is why we can detect synchrotron radiation from distant galaxies and nebulae. It's a brilliant beacon signaling the presence of powerful magnetic fields and ultra-relativistic particles. The light emitted can range from low-energy radio waves up through visible light and into higher energies, painting the cosmos in a broad brushstroke of radiation. Another key process is known as Bremsstrahlung, a German word meaning breaking radiation. This occurs when a fast-moving charged particle, like an electron, approaches a much heavier object, such as an atomic nucleus. The powerful electric field of the nucleus acts as a brake, causing the electron to rapidly decelerate. Just as acceleration produces light, so does this sudden slowdown. The kinetic energy the electron loses in that encounter is instantly converted into a photon of light. The greater the deceleration, the higher the energy of the emitted light. In the hot, dense plasma of a solar flare or the accretion disk around a black hole, this process generates everything from X-rays to intense gamma rays, providing a stark, high-energy portrait of particle collisions. The true wonder is the sheer range of light these processes can create. It's not just the visible light our eyes can see. This magnetic particle acceleration generates a full spectrum of electromagnetic radiation. From the long, rolling waves of radio energy that travel across galaxies to the incredibly short, powerful bursts of gamma rays that signal the most violent events in the universe, it's all connected to this fundamental dance between charged particles and magnetic forces. The spectacular cosmic light shows we observe through telescopes are literally the glow from this subatomic chaos, a direct translation of magnetic turmoil into a language of light that we can finally see and interpret. To witness magnetic fields spiraling into absolute chaos, we need look no further than our own sun. Solar flares are arguably the most dramatic and well-documented examples of this explosive process in action. The sun is not a placid ball of fire. It's a seething, dynamic sphere of superheated plasma, and its surface is a constantly shifting tapestry of powerful magnetic fields. These fields are generated by the churning motion deep within the sun, and they often become twisted and contorted, rising up through the solar surface to form visible features we call sunspots. These dark patches are actually portals to immense magnetic intensity, and the regions around them are where the stage is set for a spectacular breakdown. When these magnetic fields become too tangled and strained, stretched like over-tightened rubber bands across tens of thousands of miles, they can no longer maintain their structure. This is the trigger for a solar flare. The event begins with a sudden and catastrophic reconnection of magnetic field lines. In a frantic, explosive reorganization that lasts mere minutes, the built-up magnetic energy is converted at an astonishing rate. This energy doesn't just vanish, it floods into the surrounding solar atmosphere, heating the local plasma to tens of millions of degrees Kelvin, and accelerating electrons and protons to nearly the speed of light. The result is a brilliant flash of light that erupts across the entire electromagnetic spectrum, from radio waves to visible light and up into the most energetic X-rays and gamma rays. A single, large flare can briefly outshine the entire sun in certain wavelengths of light, releasing more energy than 1 billion megatons of TNT. The effects of this magnetic mayhem are not confined to the sun. The most powerful flares hurl vast clouds of charged particles, known as coronal mass ejections, out into the solar system. When these clouds are directed at Earth, they can have significant consequences. Our planet's magnetic field does a heroic job deflecting most of this onslaught, but the sheer force of a major event can still overwhelm our defenses. The most famous historical example is the Carrington event of 1859. Named after the astronomer who observed the initial solar flare, this colossal geomagnetic storm caused auroras so intense they were seen as far south as the Caribbean. Imagine the night sky near the equator glowing a terrifying, brilliant red. The technology of the time was simple, yet the storm induced powerful electrical currents in telegraph lines. Operators received shocks from their equipment, telegraph papers caught fire, and some systems continued to send messages even after being disconnected from their power sources. In our modern, technologically dependent world, a similar event today would be far more catastrophic. It could induce destructive currents in our power grids, leading to widespread and prolonged blackouts. It could cripple satellites, disrupting global positioning systems, telecommunications, and weather monitoring. it would pose a serious radiation risk to astronauts and even to passengers and crew on high-altitude flights. This is precisely why understanding solar flares is so critical. It's not just an academic pursuit. By studying the magnetic instabilities that lead to these eruptions, scientists working in the field of space weather aim to improve our forecasting abilities. With better warning, we could potentially safeguard transformers in our power grid, put satellites into safe mode, and reroute air traffic, turning a potential global technological disaster into a managed and fascinating natural event. This intense study of our sun's tantrums provides a crucial blueprint for understanding how the same fundamental magnetic processes unfold on an even grander scale elsewhere in the cosmos. While our sun provides a stunning example of magnetic fury from a distance, we have our own front row seat to a far more personal and poetic display of this cosmic dance. High above our heads, in the thin, cold air near the edge of space, Earth's magnetic field engages in a constant, gentle struggle with the solar wind. This interaction doesn't always end in violent disruption. Sometimes it culminates in one of nature's most breathtaking performances, the aurora. These shimmering curtains of green, violet, and red that dance across the polar skies are far more than just pretty lights. They are a direct, visible manifestation of magnetic fields channeling chaos into creation, a silent sonnet written in charged particles and excited atoms. The entire process begins some 93 million miles away, with our sun constantly exhaling a stream of charged particles, a plasma of electrons and protons known as the solar wind. This wind blows past Earth at speeds of nearly 1 million miles per hour, carrying with it the sun's own magnetic field. When this gust of solar material reaches our planet, it doesn't hit a solid wall. Instead, it encounters Earth's protective magnetic bubble, the magnetosphere. Our planet's magnetic field acts like a shield, deflecting the bulk of the solar wind around it, much like a rock diverting the flow of a stream. But this interaction is far from perfect. It's a dynamic and often turbulent negotiation between two powerful magnetic forces. On the side of Earth facing away from the sun, our magnetosphere is stretched out into an incredibly long magnetic tail, millions of miles in length. It is deep within this elongated region, under the immense pressure of the flowing solar wind, that the magic of magnetic reconnection occurs. The stretched and stressed field lines in the tail snap and realign, acting like a colossal slingshot. This process violently accelerates countless electrons, hurling them back down along the planet's magnetic field lines with tremendous energy. These energized particles are then funneled by the magnetic field's shape toward the two magnetic poles, spiraling downward into the upper atmosphere in a vast, invisible waterfall of charge. This is where the invisible becomes visible. As these high-speed electrons plunge into the thin air, 60 to a few hundred miles above the ground, they begin to collide with the atoms and molecules of our atmosphere, primarily oxygen and nitrogen. These collisions are a transfer of energy. The incoming electron strikes a gas atom, exciting it by bumping one of its own electrons into a higher energy level. Almost instantly, that excited electron drops back down to its normal state, and to do so, it must release that extra energy it just absorbed. It releases that energy in the form of a tiny packet of light, a photon. Each individual collision produces just one photon, but multiplied by billions upon billions of collisions happening every second across vast swaths of the sky, the effect is a brilliant, glowing canopy of light. The specific color of the aurora is a direct chemical report from the upper atmosphere. The most common hue, a brilliant pale green, comes from oxygen atoms located about 60 miles high, which emit light at this specific wavelength when struck by energetic particles. The rarer, deep crimson reds come from higher altitude oxygen, over 150 miles up, which emits a different shade under more rarefied conditions. Meanwhile, nitrogen molecules can contribute stunning blues and purples, especially at the lower edges of the most vibrant displays. The shape of the aurora, whether it appears as gentle arcs, rippling curtains, or racing rays, is a direct visual map of the complex, shifting lines of force in Earth's magnetic field at that very moment. What makes the aurora such a profound example of magnetic phenomena is its accessibility. It is a cosmic event that we can witness with our own eyes, a gentle echo of the same violent reconnection processes that power solar flares and stellar eruptions across the galaxy. They are a beautiful and humbling reminder that the forces shaping the universe are not abstract concepts confined to distant space. They are active, dynamic processes that literally illuminate our own sky, connecting each of us personally to the vast, magnetic heartbeat of our sun and the intricate protective embrace of our own planet. This elegant interplay between solar output and planetary magnetism sets the stage for understanding how these same principles operate in even more extreme and powerful environments. Yet for all their raw power, even the mightiest magnetic fields of a neutron star can be pushed into instability. The incredible rotational energy and the crushing gravity work together to twist and contort these fields, creating regions of immense stress. In the polar regions of the star, where the magnetic field lines are funneled into a tight, focused beam, this instability finds its most spectacular outlet. Charged particles accelerated to near-light speeds along these open field lines are forced to emit light through the synchrotron process we discussed earlier. The result is not a gentle, omnidirectional glow, but a searingly intense, narrow beam of radiation shooting out from each magnetic pole. It is a literal lighthouse beacon forged from magnetic chaos, and if that beam happens to sweep across our line of sight here on Earth, we witness one of the most precise clocks in the universe, a pulsar. That regular ticking signal is what astronomers first detected in 1967, a discovery so perfectly timed and artificial searching that it was briefly nicknamed LGM for Little Green Men. We now know these pulsars are not alien signals but the spinning beacons of neutron stars. Each time the star rotates, its beam sweeps past us, and we register a pulse of energy that can be detected across the electromagnetic spectrum, from radio waves to gamma rays. The incredible stability of this pulse is a direct testament to the neutron star's mind-boggling density. It's a spinning ball of matter so perfectly smooth and rigid that its rotation is more stable than even our most advanced atomic clocks. The existence of these signals alone tells us that the process of creating light from magnetic acceleration is not only possible, but can operate with machine-like precision in the most extreme gravitational environments imaginable. By studying the subtle variations in these pulses, how they slow down over millennia or occasionally experience a sudden glitch in their timing, scientists can probe the interior physics of these exotic objects and the behavior of their superfluid cores. More importantly for our story, the pulsar beam itself is a direct observation of light being generated by a spiraling, out-of-control magnetic field. It shows us that even in a place where matter is crushed into its most extreme form, the fundamental laws of physics still hold true. Accelerate a charged particle in a magnetic field, and it will release light. This profound discovery not only deepens our understanding of cosmic magnetism, but also perfectly sets the stage for the next chapter, where these same processes are taken to an even more violent and universe-shaking extreme. But if the fury of a solar flare seems immense, or the clockwork precision of a pulsar appears powerful, then gamma-ray bursts truly redefine the very meaning of cosmic energy. These are the universe's most violent, most explosive events since the Big Bang itself. For a few fleeting seconds, a single gamma-ray burst can outshine every star in 100 billion galaxies combined, focusing more energy into a narrow beam than our Sun will release across its entire 10 billion-year lifetime. And at the heart of this almost unimaginable detonation lies the same fundamental process we've been exploring: magnetic fields spiraling into absolute catastrophic mayhem. The story of a typical long-duration gamma-ray burst begins with the death of a truly massive star, many times heavier than our Sun. Having burned through its nuclear fuel, the star's core can no longer support its own immense weight. It collapses catastrophically inward, not into a neutron star, but into a black hole. As this happens, the star's outer layers come crashing down after it, only to rebound off the newly formed, ultra-dense core in a titanic shockwave. This is the supernova explosion, but that's only the beginning. What follows is a phenomenon that scientists call a collapsar. As more and more material continues to rain down onto the newborn black hole, it doesn't just fall in directly. It forms an incredibly hot, rapidly spinning disk of plasma, an accretion disk whirling a Chinese letter light speeds just outside the event horizon. It is within this maelstrom that magnetic chaos reaches its apex. The magnetic fields inherited from the original star are caught in this furious whirlpool of superheated matter. They are stretched, amplified, and wound up to incredible intensities, much like twisting a rubber band until it screams with tension. In this environment, the conditions are perfect for the mother of all magnetic reconnection events. The fields, unable to sustain their twisted configuration any longer, snap and realign with explosive force. This reconnection does two things simultaneously. First, it acts as a powerful engine, helping to blast two narrow, oppositely directed jets of material outward from the poles of the accretion disk. These jets, composed of plasma and radiation, are accelerated to more than 99.99% of the speed of light. Second, the reconnection process itself within these jets acts as a direct particle accelerator on a cosmic scale, hurling electrons to ultra-relativistic speeds. It is within these narrowly focused jets that the gamma-ray light is born. The electrons, accelerated by the reconnecting magnetic fields, are then forced to spiral along the jet's own powerful magnetic field lines. This sudden, violent acceleration forces them to emit radiation through the synchrotron process, but at energies so extreme that the light produced is not visible, not even X-rays. It is the highest energy form of light in the universe, gamma radiation. For those few precious seconds, if one of those jets is pointed directly at Earth, our satellites detect a spectacular, blinding flash of gamma rays that briefly dominates the entire high-energy sky. There is another, even more extreme pathway to a gamma-ray burst, the merger of two neutron stars. When these incredibly dense stellar corpses spiral into each other after billions of years in a gravitational dance, their collision is another crucible for magnetic madness. As they merge, they can form, for a brief instant, a hypermassive neutron star with a magnetic field trillions of times stronger than Earth's, which is then itself likely to collapse into a black hole. The resulting turbulence and shockwaves can also launch ultra-relativistic jets, where magnetic reconnection again plays a key role in particle acceleration and light creation. It was the detection of gamma rays and gravitational waves from such an event in 2017 that confirmed this theory and opened a whole new window into multi-messenger astronomy. Studying these brief, brilliant flashes is like looking directly into the engine room of cosmic catastrophe. By analyzing the light curves and spectra of gamma-ray bursts, astronomers can work backwards to understand the physics driving the jets, the role of magnetic reconnection in powering them, and the incredible efficiencies of these natural particle accelerators. These events are not just destructive, they are also creative. The same jets that create the gamma-ray burst are also thought to be the factories where many of the heaviest elements in the universe, like gold and platinum, are forged through rapid neutron capture. In a very real sense, the magnetic chaos that creates a gamma-ray burst also seeds the cosmos with the materials needed to build new planets and, ultimately, life itself. We've seen how magnetic turmoil creates light on scales from our solar system to the explosive death of stars, but these forces also operate on the grandest stage of all, the architecture of entire galaxies. It turns out that the invisible threads of magnetism are master weavers in the cosmic tapestry, silently shaping the birth, life, and ultimate form of the galaxies we observe. Their influence is subtle, pervasive, and absolutely fundamental, acting as a guiding hand on the gas and dust that are the raw materials for everything we see. A galaxy begins its life not as a collection of stars, but as an immense collapsing cloud of primordial gas, mostly hydrogen and helium. As this vast cloud condenses under its own gravity, it begins to spin and flatten into a disk. But gravity alone doesn't dictate the final structure. Weak magnetic fields present even in the early universe are caught up in this flow. As the gas moves, these seed fields are stretched and amplified, much like a piece of taffy being pulled into long, thin strands. These magnetic field lines then act as a cosmic scaffold. They can channel the flow of gas, preventing it from collapsing chaotically in all directions at once. They introduce a kind of order to the chaos of creation, helping to define the rotation of the galactic disk and the formation of its distinct spiral arms. Within a mature galaxy like our own Milky Way, magnetic fields are everywhere, threading the space between the stars. This interstellar medium is far from empty. It's a complex ecosystem of cold, dense gas clouds and hot, diffuse plasma. Magnetic fields permeate it all, and their pressure is a powerful force. They can provide crucial support to a massive cloud of gas that is on the verge of collapsing to form new stars. By exerting an outward pressure, they can actually resist the inward pull of gravity, putting a temporary brake on star birth. For a star to be born, the cloud must become dense enough to overcome not just thermal pressure, but magnetic pressure as well. This often happens through a slow, cosmic process where the magnetic field lines gradually slip away from the gas particles, allowing the final, critical collapse to begin. Conversely, these same fields can also trigger star formation. When galactic magnetic fields themselves become turbulent, shocked by the blast wave from a nearby supernova, or twisted by the gravitational interaction with a passing galaxy, that chaos can compress vast sheets of gas. Imagine a wrinkled carpet being smoothed out. The wrinkles bunch up material as they move. In a similar way, turbulent magnetic fields can create dense knots and filaments within gas clouds, pushing enough material together to tip the balance and ignite the furnace of a new star. This duality makes magnetism a galactic regulator, a force that can both suppress and stimulate the creation of new suns, directly controlling the evolution of a galaxy over billions of years. Nowhere is the visible hand of magnetism more apparent than in the graceful arms of a spiral galaxy. Radio telescope observations have revealed something astonishing. The magnetic field lines in these galaxies are not random. They closely follow the intricate patterns of the spiral arms themselves. It's as if the galaxy has traced its own luminous structure with invisible magnetic ink. This alignment isn't a coincidence, it's a dynamic partnership. The differential rotation of the galaxy, the fact that stars and gas at different distances from the center orbit at different speeds winds up the magnetic field like a clock spring, stretching and aligning it with the spiral density waves that define the arms. This ordered magnetic field then helps to maintain the structure of the arms, guiding ionized gas along its length and contributing to the stunning symmetry we observe. But this order can also break down, leading back to the brilliant chaos we know so well. Within those spiral arms, the very stars whose birth was influenced by magnetism eventually die. A massive star ending its life in a supernova explosion does more than just unleash a torrent of light and newly forged elements. It injects incredible turbulence into the surrounding magnetic field. The blast wave expands outward, compressing and distorting the galactic magnetic field in its vicinity. This can trigger new rounds of star formation nearby, but it also demonstrates the continuous feedback loop between magnetism and light. The supernova's light is a direct product of stellar processes, but its effect on the magnetic environment helps to write the next chapter in the galaxy's story. This profound interplay is why astronomers now consider magnetic fields an essential ingredient in our cosmological models. We can no longer understand galaxy formation through gravity and gas dynamics alone. To truly comprehend how galaxies evolve from the early universe to the present day, how they recycle their material to form successive generations of stars, and why they take the beautiful shapes they do, we must account for the silent, pervasive force of magnetism. It is a cosmic sculptor whose tools are invisible, but whose finished work is illuminated by the very starlight it helped to create. Of course, we can't travel to the heart of a solar flare or stand beside a merging neutron star to watch magnetic fields unravel in real time. But what if we could bring a piece of that cosmic chaos right here to Earth? This is precisely the goal of some of the world's most advanced laboratories, where scientists are building miniature universes in metal chambers to dissect the secrets of magnetic instability. By recreating these astronomical processes under controlled conditions, researchers are doing more than just testing theories. They are building a fundamental bridge between the abstract mathematics of astrophysics and the tangible, observable reality of experimental science. The primary stage for these experiments is a superheated, ionized gas known as plasma, the same state of matter that makes up stars, nebulas, and the vast spaces between galaxies. To contain and study this seething fourth state of matter, scientists use ingenious devices like tokamaks. These are massive, donut-shaped chambers wrapped in powerful magnetic coils. Inside a tokamak, a relatively small amount of hydrogen gas is heated to temperatures exceeding 100 million degrees Celsius, far hotter than the core of the Sun. At these extremes, the gas becomes a plasma, and the magnetic fields generated by the surrounding coils take control, suspending the glowing, pinkish matter in a perfect, levitating ring, preventing it from ever touching and vaporizing the metal walls. But stability is not the end goal here. It's the prelude to chaos. Researchers deliberately push the conditions within the tokamak to their breaking point. They increase the electrical current flowing through the plasma or tweak the external magnetic fields, carefully nudging the system toward instability. And just as in the cosmos, the plasma rebels, the magnetic field lines that were once holding everything in a smooth, orderly torus begin to kink, twist, and contort. They can suddenly snap and reconnect in a violent, microscopic burst of energy, a perfect laboratory-scale replica of the magnetic reconnection that powers solar flares. High-speed cameras and sensitive magnetic probes record every detail of this event, measuring exactly how much energy is released, how fast particles are accelerated, and what kind of light is emitted. This data is pure gold for astrophysicists, providing them with hard numbers to plug into their models of stellar and galactic phenomena, transforming educated guesses into validated physical principles. Another powerful tool in this quest is the high-energy laser. At facilities like the National Ignition Facility in the United States or the Laser Megajoule in France, scientists can recreate the extreme conditions found in astrophysical events, not with large, sustained magnetic fields, but with unimaginably intense and focused pulses of light. They aim an array of powerful laser beams at a tiny target, often a small pellet of hydrogen or a specially crafted metal foil. In a fraction of a billionth of a second, the surface of the target is vaporized, exploding outward and in accordance with Newton's third law, driving the rest of the material inward with immense force. This process creates a tiny, fleeting pocket of matter that is incredibly hot and dense, mimicking the environment near a black hole's accretion disk or at the heart of a giant planet. Within this microscopic fireball, magnetic fields are born and amplified from virtually nothing through a process called the Biermann battery effect. As the laser-driven plasma expands, differences in temperature and pressure create swirling electric currents, which in turn generate magnetic fields. These fields are then stretched and twisted by the turbulent plasma motions, just as they are in deep space. Researchers can use these laser-produced plasmas to study how magnetic fields grow from tiny seeds into dynamically important forces, and ultimately, how they become unstable and influence the behavior of the entire system. The entire event might last only nanoseconds, but advanced diagnostics can capture it all, providing a slow-motion view of cosmic magnetic genesis. The implications of this research stretch far beyond satisfying our cosmic curiosity. The foremost application is in the pursuit of fusion energy, the dream of harnessing the power of the sun here on Earth. The same magnetic instabilities that scientists are trying to create and study in tokamaks are the very ones that can sabotage a fusion reaction. If a large-scale reconnection event or a major instability occurs in a future power plant, it could dump a huge amount of energy onto the reactor walls, causing damage and quenching the fusion process. By learning to predict, control, and ultimately suppress these instabilities, researchers are literally paving the way for a revolutionary source of clean, limitless energy. Every experiment that tames a piece of magnetic chaos is a step closer to lighting our cities with miniature stars. Furthermore, this work provides an invaluable service to astronomy. A telescope can only show us the light that arrives from a distant event. It can't show us the intricate dance of magnetic fields that created it. Laboratory experiments act as a Rosetta Stone, allowing us to decode the light signatures we see in the cosmos. By measuring the specific spectrum of light emitted during a controlled magnetic reconnection event in a lab, scientists can directly compare it to the light collected from a solar flare or a distant nebula. If the signatures match, it provides powerful, direct evidence that the same physical process is at work across the vastness of space. This turns astrophysics from a science of passive observation into one of active experimentation, where we can test the laws of the universe not just by looking at it, but by touching a piece of it right here at home. Long before we had satellites to monitor solar storms or supercomputers to model plasma turbulence, the fundamental connection between magnetism and light was being uncovered through sheer human curiosity and ingenious experimentation. This journey of discovery didn't begin in a high-tech lab. It started with simple observations of the natural world, like the strange way a compass needle twitched during an auroral display, or how a spark from a static electricity machine could make a nearby magnet vibrate. It was through patiently unraveling these mysteries that a few brilliant minds laid the entire foundation for our modern understanding of cosmic light shows. Perhaps no single figure was more pivotal in this story than the Scottish physicist James Clerk Maxwell. In the 1860s, Maxwell took a set of disparate experimental laws describing electricity and magnetism. the work of pioneers like Michael Faraday and André Marie Ampère, and wove them into a single, elegant, and breathtakingly powerful mathematical framework. His now famous set of 20 equations, later distilled into the 4 we know today, did something revolutionary. They proclaimed that electricity and magnetism were not two separate forces, but two intimately linked aspects of a single phenomenon, electromagnetism. But Maxwell's genius didn't stop there. As he manipulated his equations, he found something astonishing lurking within the math: a wave. This theoretical wave traveled at a specific, calculable speed, and when Maxwell crunched the numbers, he found its velocity was exactly equal to the known speed of light. In an incredible leap of insight, he proposed that light itself was nothing more than an electromagnetic wave, a propagating disturbance in intertwined electric and magnetic fields, each one generating the other in a self-sustaining dance through empty space. This was the ultimate unification. It meant that the shimmer of a candle flame, the blinding flash of a solar flare, and the invisible warmth of a hearth were all the same fundamental phenomenon, all governed by the same set of laws. Maxwell had provided the mathematical proof that a changing magnetic field could indeed create an electric field, and a changing electric field could create a magnetic field, and together they could race outward as light. While Maxwell was working out the theory in his Cambridge study, a daring Norwegian scientist named Christian Birkeland was braving the Arctic cold to prove it in practice. He was obsessed with the Aurora Borealis, and he refused to accept the prevailing theory that they were simply reflections of sunlight off Arctic ice. Birkeland suspected they were connected to the newly discovered corpuscular rays from the sun, what we now call the solar wind. To test his radical idea, he mounted a remarkable expedition, building observation outposts across Norway's northern latitudes to meticulously map the auroral currents. But his most famous contribution happened back in his lab in Oslo. There, he created a scaled-down version of Earth. He placed a magnetized metal sphere, which he called a tarella, or Little Earth, inside a large vacuum chamber. Then he bombarded it with beams of electrons. The result was stunningly clear and beautiful. The electrons were guided by the sphere's magnetic field directly toward its poles, where they struck a thin gas residue in the chamber, causing it to glow with eerie, shimmering rings of light around the magnetic poles. He had, right there on his tabletop, created an artificial aurora. This experiment was the first direct demonstration that charged particles from space, channeled by a planet's magnetic field, could indeed generate light in an atmosphere. Birkeland's work provided the crucial experimental evidence that connected the solar wind, Earth's magnetism, and the ethereal glow of the northern lights into a single, coherent physical story. These two pioneers, one a theorist and the other an experimentalist, set the stage for everything that followed. Maxwell gave us the universal laws, and Birkeland showed us how they played out on our own planet. Their work, often underappreciated in their own time, proved that the cosmos operates on principles we can understand, test, and even recreate. They transformed the aurora from a mysterious spirit dance into a measurable plasma physics experiment, and light itself from a mere visual phenomenon into the primary messenger of the universe, carrying information about the magnetic chaos that created it. This legacy of curiosity and rigorous investigation is the bedrock upon which all modern astrophysics is built, turning the wildest speculations about magnetic fields in space into a science we can truly explore. Today's astronomers are no longer passive observers of these magnetic dramas. They have front-row seats to the most violent and beautiful events in the cosmos, thanks to an arsenal of telescopes so advanced they border on the magical. These instruments act as our extended senses, allowing us to see the invisible and capture the fleeting moments when magnetic fields snap, twist, and ignite. At the forefront of this effort is the Solar Dynamics Observatory, or SDO, a spacecraft entirely dedicated to staring unblinkingly at our sun. It doesn't just take pretty pictures, it captures high-resolution images in multiple wavelengths of light simultaneously, every 10 seconds around the clock. This means scientists can watch a solar flare unfold not as a single flash, but as a complex, evolving ballet of magnetic fields. They can see the precise moment of magnetic reconnection in the sun's corona, track the subsequent tsunami of superheated plasma rushing across the solar surface, and correlate it all with the intense bursts of X-ray and ultraviolet light being emitted. This constant vigil provides an unprecedented data stream, turning each solar eruption into a detailed case study that helps refine our computer models of plasma behavior and magnetic instability. But our vision extends far beyond our own solar system. The Event Horizon Telescope, famous for capturing the first image of a black hole, is another powerful tool for studying magnetic chaos, albeit in a very different way. The EHT isn't a single telescope. It's a global network of radio observatories that work together as one Earth-sized instrument. This gives it the incredible resolution needed to study the frenetic environment just outside a black hole's event horizon. There, in the swirling accretion disk of doomed matter, magnetic fields are amplified to unimaginable strengths. The EHT can detect the faint synchrotron radiation emitted by electrons spiraling along these field lines, allowing scientists to map the magnetic field structure itself. This is how we're beginning to understand the role of magnetism in powering the relativistic jets that scream away from black holes at near light speed. We are literally mapping the magnetic architecture of chaos, seeing how these fields channel and focus some of the most powerful outflows in the universe. The true power of modern astronomy, however, lies in its multi-wavelength approach. A gamma-ray burst observed by the Fermi Gamma-Ray Space Telescope tells us about the initial cataclysmic explosion and the particle acceleration within the jet. But that's only part of the story. Follow-up observations with the Hubble or James Webb Space Telescopes capture the fading afterglow in visible and infrared light, which reveals the chemistry of the surrounding environment and the distance of the event. Meanwhile, radio telescopes like the Very Large Array can study the longer-lasting radio remnant, telling us about the interaction between the jet and the interstellar medium. By stitching together these observations across the entire electromagnetic spectrum, we get a complete three-dimensional movie of a magnetic catastrophe. Each wavelength of light provides a different chapter of the story, from the initial violent reconnection to the lingering aftermath. This flood of data is doing more than just confirming old theories. It's constantly presenting us with new puzzles and surprises. For instance, observations of solar flares frequently show features that our current models of magnetic reconnection can't fully explain, suggesting that the process is even more complex and efficient than we thought. Data from neutron stars has revealed sudden, dramatic changes in their magnetic fields, events nicknamed anti-glitches, which challenge our understanding of matter under extreme conditions. Each anomaly, each unexpected reading, is a clue that pushes our knowledge forward, forcing us to refine our simulations and sometimes to rethink fundamental assumptions. The technology doesn't just provide answers, it inspires better questions, ensuring that our journey to understand the magnetic universe remains a dynamic and ever-evolving adventure. To truly grasp the invisible forces sculpting solar flares and pulsar beams, we need more than just powerful telescopes. We need a mathematical language that can describe the complex dance between magnetic fields and superheated matter. This is where the elegant framework of magnetohydrodynamics, or MHD, comes into play. Think of MHD as a set of rules that combines the laws of magnetism from James Clerk Maxwell with the laws of fluid motion from classical physics. It treats a plasma, that seething, electrically charged gas found in stars and nebulas, not as a collection of individual particles, but as a single, continuous fluid that can carry and be shaped by magnetic fields. This powerful fusion allows scientists to write down equations that describe how a magnetic field can be frozen into a flowing plasma, stretched like taffy, or suddenly snap and release its pent-up energy. It's the fundamental playbook for predicting how order can descend into magnificent chaos. With these equations in hand, researchers can move from theory to breathtaking virtual recreation using supercomputers. These aren't simple animations, they are massive computational simulations that divide a volume of space, like the sun's corona or the environment around a neutron star, into billions of tiny digital cells. For each cell, the computer solves the complex MHD equations, calculating how the plasma density, temperature, velocity, and magnetic field strength change over infinitesimally small steps in time. Running these calculations for millions of steps allows us to watch a solar eruption unfold over hours or days in a simulation that might take a supercomputer weeks to process. The result is a stunningly detailed movie of a magnetic catastrophe, showing the precise moment when twisted field lines become unstable, reconnect, and launch a tsunami of energy and light into space. These simulations don't just illustrate what we think happens, they offer specific, testable predictions about the amount of energy released, the types of light emitted, and the speed of the ejected material, which can then be compared directly with real observations from satellites and telescopes. Yet for all their power, these models are continually being refined because nature always has a way of revealing deeper layers of complexity. One of the most significant challenges is accurately capturing the phenomenon of turbulence. In a real plasma, motion occurs across a vast range of scales, from massive flows larger than a planet down to tiny eddies on the subatomic level. It's computationally impossible to simulate every single one of these scales simultaneously, even with our most advanced machines. So scientists must employ clever approximations, developing sub-grid models that estimate the net effect of these tiny, unresolved turbulent motions on the larger system. Getting this right is crucial because turbulence doesn't just add background noise. It can dramatically enhance the rate of magnetic reconnection, effectively determining how quickly and explosively a magnetic field can unravel. It's the difference between a slow, sizzling leak and a world-shattering detonation. Despite these challenges, the success of MHD is undeniable. It was a computational MHD model that first convincingly showed how the kink instability, a process where a magnetic flux rope twists itself into a coil until it violently snaps, could trigger a solar flare. These same models are used to understand the precise clockwork mechanism of pulsars, simulating how their incredibly strong magnetic fields can accelerate particles to create those lighthouse-like beams of radiation. Furthermore, this work has incredibly practical applications right here on Earth. The entire design of tokamak fusion reactors, which aim to harness the power of the stars, relies on MHD to predict and control the behavior of the hot plasma confined by magnetic fields, striving to keep it stable long enough to achieve ignition. The ongoing dialogue between these theoretical models and real-world observations is what drives the field forward. Every time a spacecraft like the Parker Solar Probe flies through a solar eruption and returns data that matches an MHD simulation's prediction, it's a triumphant validation of our understanding. And when the data doesn't match, it's not a failure but an exciting discovery, pointing the way toward a new physical process or a needed refinement in the model. perhaps accounting for particle effects that pure fluid models miss. This iterative process of prediction, observation, and refinement is how we slowly decode the universe's most powerful magnetic mysteries, transforming brilliant chaos into comprehensible order. Yet for all the power of our simulations and the clarity of our theories, there remains a humbling frontier in this field, the sheer difficulty of prediction. We understand the basic script of how a magnetic field can spiral into chaos, but forecasting the precise timing and intensity of that breakdown is a challenge of monumental proportions. This isn't a shortcoming of our science, but rather a reflection of the deeply complex and nonlinear nature of the systems we're trying to model. In a plasma, every action can have a cascade of reactions, where a tiny, seemingly insignificant fluctuation in one area can amplify into a system-wide eruption elsewhere. It's the ultimate butterfly effect playing out in superheated gas and unimaginably powerful magnetic forces, making long-term prediction incredibly fraught. This challenge becomes starkly clear in the very practical field of space weather forecasting. Teams of scientists at organizations like NOAA Space Weather Prediction Center work tirelessly to monitor the sun, using a fleet of satellites to track sunspot regions and measure magnetic field strength. They can identify regions that are primed for a flare, areas where the magnetic field is twisted and packed with energy like a coiled spring. They can issue warnings that a flare is likely within the next 24 or 48 hours. But pinpointing the exact moment it will happen, whether in the next 5 minutes or the next 5 hours, remains beyond our current capabilities. The final trigger is often a small-scale instability that our present instruments simply cannot resolve from 93 million miles away. This imprecision has real-world consequences. A false alarm can lead satellite operators to unnecessarily put their valuable assets into safe mode, temporarily disrupting communications and data services. A missed prediction, however, could mean a multi-billion-dollar communications satellite is caught unprepared by a blast of high-energy particles, potentially suffering permanent damage to its sensitive electronics. The root of the problem lies in the vast range of scales involved, from the astronomical down to the microscopic. A solar flare might erupt from an active region larger than Earth itself, but the initial magnetic reconnection that sets it off can occur in a volume of space just a few kilometers across. Our global models of the Sun's magnetic field cannot possibly simulate such fine detail across the entire solar disk. It would require computational resources far beyond what currently exists. Furthermore, the behavior of the plasma at these smallest scales is governed not just by the fluid-like laws of magnetohydrodynamics, but by the intricate dance of individual particles, a realm known as kinetic physics. This requires an entirely different, even more complex set of equations to describe. Bridging this gap, creating a model that seamlessly integrates the global fluid behavior with the local particle physics, is one of the grandest challenges in modern plasma astrophysics. This isn't just an academic puzzle. Improving our predictive ability is a critical step toward building a more resilient technological society. With better warning, we could more reliably safeguard our power grids from induced currents, protect astronauts from radiation exposure, and ensure the continuous operation of the global positioning and satellite communication systems that modern life depends upon. Every failed prediction and every unforeseen solar storm provides a new set of data, another clue that helps researchers refine their models and inch closer to truly understanding the tipping point between magnetic order and luminous chaos. This relentless pursuit of predictability forces us to ask even deeper questions about the fundamental nature of our universe and whether some of its most magnificent displays of power are, at their heart, inherently unpredictable. The profound understanding we're gaining from magnetic research extends far beyond the realm of pure science, weaving itself directly into the fabric of our daily lives and our collective future. On the most practical level, this knowledge is our first and best line of defense against one of nature's most potent threats: severe space weather. A major coronal mass ejection, propelled by a massive solar flare, has the potential to induce devastating electrical currents in our planet's crust. These geomagnetically induced currents can overload and destroy the massive transformers that form the backbone of our national power grids, potentially causing blackouts that could last for months and affect millions of people. By improving our models of solar magnetic instability, we move from vague warnings to precise forecasts. This gives grid operators crucial time to implement protective measures, like placing systems in safe mode or managing load, effectively allowing us to shield our technological civilization from a celestial tantrum. This isn't theoretical. Space weather forecasters already use these insights to issue alerts that protect satellites, aviation, and energy infrastructure every single day. Perhaps the most transformative practical application lies in the quest for clean, limitless energy through nuclear fusion. The entire concept of a tokamak or stellarator reactor is to use immensely powerful magnetic fields as an invisible bottle to contain a star in a bottle, a superheated plasma where fusion can occur. The primary obstacle to sustaining this reaction is the tendency of that plasma to develop instabilities, where magnetic field lines kink, twist, and break containment in a fraction of a second, instantly quenching the reaction and potentially damaging the reactor vessel. Every breakthrough in understanding astrophysical magnetic turbulence directly feeds into solving this engineering nightmare. Researchers are using knowledge gleaned from studying solar flares to design smarter magnetic coils and feedback systems that can detect and suppress these instabilities before they can grow. Success here wouldn't just be a scientific victory. It would be a global game-changer, offering a fundamentally new source of baseload power that could help address climate change and energy poverty. Yet, with this growing power to understand and manipulate magnetic forces comes a weighty ethical responsibility. As our ability to model and control plasma improves, so does the potential for applications that venture into the controversial realm of geoengineering. Some theoretical proposals have suggested that deploying vast arrays of superconducting magnets in orbit could, in theory, be used to manipulate Earth's magnetosphere, potentially as a shield against an extreme solar storm or even in attempts to influence atmospheric patterns. The ethical dilemmas here are immense. Who gets to decide to deploy such a planet-altering technology? What are the unintended consequences of tinkering with a system as complex and globally connected as our magnetic shield? Could efforts to protect one region of the planet inadvertently weaken the magnetic field over another, exposing it to increased radiation? The history of technology is littered with solutions that created new, unforeseen problems, and the scale of magnetic geoengineering demands a global conversation about precaution, governance, and the wisdom of manipulating the very forces that make our world habitable. This tension between innovation and responsibility is a constant thread. The same fundamental physics that could lead to safe fusion energy could also, in theory, inform the development of advanced propulsion systems or even new forms of directed energy. This dual-use potential, where knowledge can be applied for both profound benefit and potential harm, requires a scientific community that is not only brilliant but also ethically vigilant. It calls for robust international cooperation and transparent dialogue with the public, ensuring that the incredible power born from understanding magnetic chaos is guided by a deep sense of stewardship for our planet and our species. Navigating this path carefully ensures that our pursuit of knowledge illuminates our future without casting dangerous new shadows. Long before we understood the physics of charged particles and magnetic fields, humanity looked up at the shimmering lights in the night sky and saw something entirely different: gods, spirits, and omens written in a language of fire. The aurora borealis and its southern counterpart are far more than scientific phenomena. They are profound cultural touchstones that have ignited the human imagination for millennia, weaving their way into our stories, our art, and our deepest sense of wonder. This celestial dance, born from invisible chaos, has consistently been interpreted as a bridge between the earthly and the divine, a canvas upon which every culture has projected its own beliefs, fears, and hopes. In Norse mythology, the flickering green lights were seen as the breath of fallen warriors or the glittering armor of the Valkyries, the shield maidens who chose which heroes would dwell in Valhalla. The Vikings believed these lights were a path to the gods, a gleaming Bifrost bridge connecting their world to Asgard. Meanwhile, the Inuit peoples of Alaska and Greenland held a rich tapestry of beliefs. Some communities saw the aurora as the spirits of their ancestors playing a game of soccer with a walrus skull across the heavens, while others believed the lights were torches held by guiding spirits helping the souls of the recently deceased find their way to the afterlife. There was also a note of caution. In some traditions, children were warned to be quiet during a display, lest the lights, interpreted as powerful and sometimes mischievous spirits, sweep down and carry them away. Across the globe, the Maori of Aotearoa, New Zealand, associated the Aurora Australis, or Tahu Nui de Macron Rangi, with campfires and reflections from the torches of their own ancestral explorers who had ventured far to the south. This interpretation of the lights as a spiritual manifestation is a global constant. In many First Nations cultures across North America, the aurora was widely viewed as the dance of celestial spirits. The Cree people called it the Dance of the Spirits, while other nations believed the lights were the reflections from giant fires lit by mighty Nanabojo, or healers. In medieval Europe, where the aurora was a much rarer sight, the displays were often met with fear and foreboding, interpreted as divine portents of war, plague, or famine, a fiery sword in the sky signaling God's displeasure. These varied interpretations, from joyous to solemn, all share a common thread, a recognition that this was no ordinary weather event. This was something transcendent, a direct communication from a realm beyond human understanding. With the Enlightenment and the gradual scientific unraveling of the aurora's mystery, the nature of its inspiration shifted but never diminished. The Romantics of the 18th and 19th centuries, in their love affair with the sublime power of nature, embraced the northern lights as the ultimate expression of terrifying beauty. Painters like Frederick Edwin Church, driven by a desire to capture nature's grandeur, traveled north and attempted to render the ephemeral light show on canvas, using glowing oils to convey the awe and majesty they felt standing beneath the shimmering curtains. Their works were not just landscapes, they were emotional experiences, attempts to freeze a moment of cosmic performance that science could explain but never truly diminish. This artistic fascination has exploded in the modern era with the advent of photography and digital media. Today, the aurora is a premier subject for photographers who brave frigid Arctic nights to capture its elusive glory. Their long exposure photographs reveal details the naked eye can barely perceive, intricate ripples, deep crimson bands, and a vivid intensity that transforms the sky into a living tapestry. These images travel across the globe in an instant, shared on social media and inspiring a new generation of sky watchers and artists. The lights have influenced filmmakers who use CGI to recreate their magic in fantasy epics, and musicians whose compositions often try to emulate their ethereal, sweeping motion. The aurora has become a universal symbol of majestic, untamable nature, a reminder that profound beauty can emerge from the most violent of cosmic processes. This deep cultural resonance does more than just produce beautiful art. It completes our understanding of these phenomena. Science gives us the how, the solar wind, the magnetosphere, the excited atoms. But culture and art give us the why it matters. They answer the human need for meaning, connection, and wonder. To stand under the aurora today is to participate in a tradition that stretches back through countless generations. You are witnessing the same display that inspired Viking poets, Inuit storytellers, and Romantic painters, all of whom tried to capture its essence with the tools they had available. This rich heritage adds a layer of profound depth to the scientific facts, transforming a plasma physics lesson into a shared human experience. It connects us not only to the cosmos but to each other across time and culture, in a collective awe of the beautiful chaos that illuminates our skies. The best part is you don't need a PhD or a multi-million-dollar observatory to witness the universe's magnetic dramas firsthand. Some of the most breathtaking displays are accessible to anyone with a little knowledge and the willingness to look up. The most iconic and accessible of these is, without a doubt, the aurora. For those living at high latitudes, think Scandinavia, Canada, Alaska, or the northern reaches of Scotland. Seeing the northern lights can be as simple as stepping into your backyard on a clear, dark winter night. But you don't have to live in the Arctic Circle to get a glimpse. During periods of intense solar activity, when a large coronal mass ejection is aimed directly at Earth, the resulting geomagnetic storm can push the auroral oval much farther south. There are well-documented accounts of these celestial curtains being visible from places like Texas, Italy, and even the Caribbean, turning a typically polar phenomenon into a rare, mid-latitude spectacle that can stop an entire city in its tracks. If dancing lights in the polar sky feel too distant, you can always turn your attention to the original source of all that magnetic energy, our sun. With a proper, specially designed solar telescope, you can safely observe the very sunspots and active regions where these colossal magnetic storms are born. These aren't your typical backyard telescopes. They are equipped with advanced filters that block over 99.99% of the sun's light, allowing you to see the intricate details of the solar surface in stunning, often orange-hued detail. You can watch as massive sunspot groups, which are essentially the footprints of intense magnetic fields breaking through the photosphere, trek across the solar disk over days. With a bit of luck and patience, you might even be there to witness a solar flare, a sudden, brilliant white flash near a sunspot group, though these events are fleeting and require being at the right eyepiece at the exact right moment. In our modern, connected world, you don't even have to rely on chance. A powerful tool for any amateur is the smartphone in your pocket. A suite of free apps and websites can turn you into a savvy space weather forecaster. Applications like Space Weather Live or NOAA Aurora Forecast provide real-time data on solar wind speed, density, and the all-important BZ component of the interplanetary magnetic field, a key indicator that, when it points south, can open the door for particles to flood into our atmosphere and trigger an auroral display. These services will send push notifications directly to your phone, alerting you when a solar flare has erupted or when a geomagnetic storm is likely to light up your local sky. This transforms the hobby from passive stargazing into an active hunt, where you're using data from NASA satellites like the Deep Space Climate Observatory a million miles away to decide whether it's worth putting on a coat and heading outside tonight. This engagement can go beyond simple observation and become a genuine contribution to science. Citizen science projects eagerly welcome data from amateurs around the globe. By submitting your photographs of auroral structures noting the time, date, and your location, you can help researchers map the altitude and intensity of a storm in ways that a single satellite might miss. Your observations from the ground provide a crucial piece of the puzzle, offering context for the data collected from space. Other projects might ask you to classify sunspot images from solar observatories or track the evolution of solar active regions. This means that a person with a modest telescope or even just a keen eye can become part of a global scientific effort, helping professional astronomers understand the nuances of our star's violent mood swings and their effects on our planet. This hands-on connection transforms abstract concepts about magnetic fields and particle physics into a tangible, personal experience, making the grand workings of the cosmos feel intimately real and deeply exciting. Witnessing these cosmic performances is one of the most thrilling ways to connect with the universe, but like any great adventure, a little preparation is the key to turning a good experience into an unforgettable one. Let's start with the most critical rule: never, ever look directly at the sun without proper protection. This isn't just about comfort, it's about permanent safety. The intense focused light of the sun can cause almost instant damage to the retina, the light-sensitive tissue at the back of your eye, and this damage is often painless and irreversible. The only safe way to view the sun directly is with filters that are specifically designed for solar observation. Internationally recognized safety standards like ISO 123-1222 ensure that eclipse glasses and solar viewers block 100% of harmful ultraviolet and infrared light and reduce visible light to a safe, comfortable level. Always inspect your solar glasses before use. If there are any scratches, punctures, or if they are older than 3 years, it's best to err on the side of caution and get a new pair. For a closer look at sunspots, you'll need a telescope equipped with a proper solar filter that fits securely over the front end of the instrument, not an eyepiece filter, which can crack under the concentrated heat. Chasing the aurora is a completely different kind of expedition, where the primary challenges come from our own planet rather than the sky. Your greatest enemy will almost always be the cold. These displays occur on clear nights, which often means plummeting temperatures, especially at high latitudes. Dressing in layers is your best strategy. Start with a moisture-wicking base layer to keep you dry. Add an insulating middle layer like fleece or wool, and finish with a windproof and waterproof outer shell. Don't forget your extremities. A warm hat, insulated gloves, and thick socks are absolutely essential. Heat is lost quickly through the head and hands, and cold feet can ruin an otherwise magical night. Good insulated waterproof boots are a worthwhile investment, as you'll likely be standing on cold, possibly snowy ground for extended periods. Finding the right location is just as important as bundling up. Light pollution is the aurora's worst foe, washing out the subtle colors and structure of the display. You'll want to get as far away from city lights as possible. Use a light pollution map to find a dark sky site, ideally with a clear view to the north if you're in the northern hemisphere, as the lights often appear low on the horizon. A wide open field, a lakeshore, or a high vantage point are all excellent choices. Safety in these remote locations is paramount. Always tell someone where you're going, and when you expect to return, charge your phone fully and consider bringing a power bank for backup. It's also wise to pack a thermos with a hot drink and some high-energy snacks. Patience is a virtue in aurora hunting, and staying fueled and hydrated makes the long wait far more enjoyable. Perhaps the most modern tool in your kit is patience and realistic expectations. The aurora can be fickle. You might wait for hours in the freezing cold only to see a faint green glow, or you might be rewarded with a sudden, explosive corona of light that dances directly overhead. Checking space weather forecasts can increase your odds, but it's no guarantee. The experience itself, standing under a canopy of stars in the profound silence of a remote night, is often its own reward, with the potential appearance of the lights being the glorious bonus. By preparing for the conditions and understanding the risks, you ensure that your quest to witness magnetic chaos made visible is safe, comfortable, and utterly rewarding. But the quest to understand magnetic chaos doesn't end with better observation. It's also being revolutionized by the power of artificial intelligence. The vast streams of data from missions like Solar Orbiter and the Parker Solar Probe are far too complex for humans to analyze in their entirety. This is where machine learning algorithms are stepping in, acting as digital detectives sifting through terabytes of information to find patterns invisible to the human eye. These AI systems are being trained to identify the subtle precursors to a solar flare or a coronal mass ejection, looking for specific magnetic field configurations that traditional models might miss. By analyzing thousands of past events, these intelligent systems can learn the unique signatures of an impending eruption, potentially giving us much longer and more accurate lead times for space weather warnings. This isn't about replacing scientists, but empowering them with tools that can handle the immense complexity and non-linear behavior of plasma, turning a flood of data into a precise forecast. The implications of this research extend far beyond satisfying our cosmic curiosity. They are deeply woven into the future of our technological civilization and our quest for sustainable energy. A more profound understanding of magnetic reconnection and plasma stability is the key to unlocking the dream of practical nuclear fusion here on Earth. In reactors like tokamaks, where superheated plasma is contained by powerful magnetic fields, the same kinds of instabilities that cause solar flares can erupt in a fraction of a second, disrupting the fusion reaction and potentially damaging the reactor vessel. Insights gained from watching how these processes unfold naturally on the Sun are directly informing the design of next-generation fusion devices. By learning how to predict, control, and ultimately suppress these destructive instabilities, we move closer to harnessing the power of the stars, offering a potential future of limitless, clean energy born from the very chaos we're striving to understand. This journey into the heart of magnetic fields is ultimately a journey to understand one of the universe's most fundamental creative processes. Every new discovery, whether from a daring spacecraft or a sophisticated computer model, peels back another layer of the mystery, revealing how the invisible architecture of magnetism shapes the visible universe. The future of this field is incredibly bright, promising not only to illuminate the darkest corners of cosmic physics, but also to light our way toward a safer and more energy-abundant world here at home. And yet, for all their cosmic grandeur, the principles of magnetic fields spiraling with purpose are not confined to the vastness of space. They are at work right here on Earth, in the most intimate and life-saving ways, connecting the physics of distant stars directly to the biology of our own bodies. Consider the incredible technology of magnetic resonance imaging, or MRI. This common medical tool is a direct application of the same fundamental principles that govern spinning neutron stars. Inside an MRI scanner, the patient lies within an immensely powerful, perfectly stable magnetic field, millions of times stronger than Earth's own. This field acts like a cosmic director, forcing the protons in the water molecules of our bodies to align with its invisible lines of force. Then, a precisely tuned pulse of radio waves is applied, knocking these tiny protons slightly out of alignment. As they snap back into place, spinning like microscopic pulsars, they release their own faint radio signals. A sophisticated computer listens to this symphony of spinning particles, translating the subtle variations in their signals into an exquisitely detailed, three-dimensional map of our inner anatomy. It is a non-invasive window into the human body, a technology that allows doctors to diagnose everything from torn ligaments to brain tumors, and it is all powered by our ability to harness and control magnetic chaos for profound good. This magnetic sense extends deep into the natural world in ways that seem almost like magic. Every year, millions of creatures from the humble monarch butterfly to the majestic humpback whale embark on epic migrations across the globe, navigating with a precision that has long baffled scientists. We now know that a key component of their internal GPS is our ability to perceive Earth's magnetic field. This sense, known as magnetoception, is nature's own version of using a compass, but far more sophisticated. Research suggests that migratory birds, for instance, might have a specialized protein in their eyes called cryptochrome. When light hits this protein, it creates a pair of molecules with entangled electrons whose quantum spin state is subtly influenced by the direction and intensity of the local magnetic field. This could potentially create a visual effect, literally allowing the bird to see the magnetic field as patterns of light and shadow superimposed on its vision, painting a navigational map across the sky that is entirely invisible to us. Other animals, like certain species of bacteria, take this a step further. They don't just sense magnetic fields, they build them. Magnetotactic bacteria are microscopic organisms that literally string together tiny crystals of magnetite, a magnetic mineral, inside their own cells, forming a perfect nanoscale compass needle. This internal magnet, called a magnetosome, passively aligns the bacterium with Earth's magnetic field lines, guiding it efficiently up or down in the water column to find its ideal oxygen level. It's a breathtaking example of biological evolution harnessing a fundamental physical force for survival, a living embodiment of magnetic navigation that is both simple and brilliant. These natural systems demonstrate that the laws of magnetism are not just abstract concepts for physicists. They are a tangible, sensory reality for countless species, a hidden layer of information woven into the fabric of their existence. This beautiful interplay between the cosmic and the biological, the physical and the living, dramatically broadens the relevance of magnetic phenomena. It shows us that the same force that carves jets of light from the chaos around a black hole also helps a sea turtle find its birthplace beach. The same principles that allow us to simulate a supernova in a supercomputer also allow a doctor to peer into a human brain without making a single incision. This interdisciplinary bridge transforms our understanding from a narrow field of astrophysics into a universal language spoken by pulsars and proteins alike. It enriches our appreciation, reminding us that the universe is deeply interconnected, and that the secrets whispered by distant magnetic fields are also written into the very blueprint of life on our own planet. One of the most persistent and understandable mix-ups about this entire process is the idea that a magnetic field can directly create light all by itself, as if the field lines themselves glow. It's a tempting image. Just twist a magnetic field and watch it light up like a neon sign. But the reality, while just as beautiful, is a bit more intricate. A magnetic field, no matter how strong or chaotic, cannot produce light on its own. It is always a master choreographer, but it needs dancers, charged particles like electrons and protons. Light is only born when these particles are forced to move, specifically when they are accelerated. Think of it like this. The magnetic field is the powerful whirlpool in a river, but the light is the spray and foam kicked up by the pebbles and debris caught in that violent current. Without those particles to accelerate, the whirlpool, for all its power, would remain invisible. This distinction is crucial because it ties every single cosmic light show, from the gentle aurora to the ferocious gamma-ray burst, back to the same fundamental rule of electromagnetism: accelerate a charge and it will radiate. This misconception often leads to another common mix-up: the belief that auroras are purely an electrical phenomenon, a simple shower of electrons streaming down from space that lights up the sky like a giant neon tube. While it's true that electric currents carried by these particles are fundamental to the process, this view completely misses the invisible director guiding the entire performance: Earth's magnetic field. Those electrons don't just rain down randomly, they are expertly funneled. The shape of our planet's magnetosphere acts like a colossal lens, focusing and steering the solar wind particles toward the magnetic poles with incredible precision. Without this magnetic guidance, those charged particles would simply splash across the entire planet, creating a faint, uniform glow everywhere instead of the concentrated, dancing curtains of light we see at high latitudes. The aurora is the spectacular result of a partnership, an electric current delivered by the solar wind, but precisely aimed and focused by Earth's magnetic embrace. Dispelling these myths does more than just correct technical inaccuracies. It deepens our appreciation for the elegant physics at play. Understanding that light requires an accelerated charge helps us see the unity behind seemingly different phenomena. The same core principle explains why a radio tower emitting waves, a toaster coil glowing red, and a distant quasar are blazing across the universe all produce light. They all involve forcing charged particles to change their motion. It's a universal recipe, and recognizing the magnetic field's role as a guide and shaper, rather than a primal source, allows us to truly appreciate its cosmic function. It is the great architect of structure in the chaos, the force that sculpts jets from black holes, shapes spiral galaxies, and paints the aurora onto our polar canvas. By clarifying these points, we move from a simplistic, almost magical view of the cosmos to a more powerful and wondrous understanding of the precise, beautiful, and knowable laws that make it all work. It's tempting to look for a simple link between the sun's fiery tantrums and our own planet's weather patterns, to imagine that a massive solar flare might directly trigger a heat wave or a hurricane down here. But the true connection is far more subtle and fascinating, operating not through daily weather but through the slow, grand tapestry of climate, and it all plays out in the thin, rarefied layers of our upper atmosphere. While the swirling winds and pressure systems that dictate our daily forecast are driven by the sun's heat and Earth's rotation, the sun's magnetic activity writes a different kind of story, one of chemistry and energy, etched in the faint traces of gas high above the clouds. This story begins when a coronal mass ejection, launched by a magnetic explosion on the sun, slams into Earth's magnetic shield. This collision doesn't just create auroras, it dumps a tremendous amount of energy into our planet's upper atmosphere, particularly in the form of energetic particles like electrons and protons. These particles don't just spiral down toward the poles. Some get trapped in the Van Allen radiation belts, while others are funneled along magnetic field lines, where they proceed to smash into the delicate soup of gases that make up our stratosphere and mesosphere. These aren't gentle collisions, they are high-impact events that can break apart stable molecules and kick off a cascade of chemical reactions. One of the most significant and well-studied effects is on Earth's protective ozone layer. Ozone, a molecule made of 3 oxygen atoms, is constantly being created and destroyed by sunlight in a natural equilibrium. But when a solar proton event delivers a surge of energy, it can dramatically accelerate the destruction side of that balance. These energetic particles smash into nitrogen and water vapor molecules, breaking them apart and creating highly reactive compounds like nitric oxide and hydrogen oxides. These compounds then act as catalysts, meaning they can destroy many ozone molecules without being used up themselves. It's like sending a tiny, destructive wrecking ball into a carefully balanced house of cards. A powerful solar storm can lead to a measurable, though usually temporary, drop in ozone concentration, particularly over the polar regions. This creates a miniature, short-lived hole in the ozone layer, allowing more of the sun's ultraviolet radiation to penetrate deeper into the atmosphere than it normally would. The impact of this doesn't stop at the ozone layer. The influx of energy from these space weather events also directly heats the upper atmosphere, causing it to expand. Think of it like blowing on a balloon. As the top of our atmosphere puffs up, it increases the atmospheric drag on the thousands of satellites and pieces of space debris orbiting Earth. This extra drag can significantly alter satellite orbits, a major concern for operators who must constantly adjust their positions to avoid collisions and maintain crucial services like GPS and communications. Furthermore, this heating can change the density and wind patterns in the upper atmosphere, which can, in very complex and indirect ways, influence the pressure gradients that drive weather systems far below. It's a bit like dropping a pebble in a pond. The ripples are largest where the stone hits, but they can travel and subtly affect the entire surface. However, and this is a crucial point, it's vital to maintain perspective on the scale of this influence. When we talk about human-driven climate change, we're talking about the overwhelming impact of greenhouse gases like carbon dioxide and methane, which trap heat radiated from the Earth's surface and are fundamentally altering the planet's energy balance. The effect of solar magnetic activity, while real and measurable, is orders of magnitude smaller and operates on a much shorter timescale. A solar proton event might cause a brief, localized change in upper atmospheric temperature or ozone levels, but it does not provide the constant, global forcing that greenhouse gases do. The Sun's 11-year activity cycle does cause a slight variation in the total solar irradiance, the sheer amount of energy the Sun emits. But this change is so small that its direct warming effect is dwarfed by the warming caused by human activity. So why does this matter? Understanding these space climate links is about more than just academic curiosity. It's about building a complete picture of our planet's complex systems. By accurately quantifying the Sun's role, we can better isolate and understand the human fingerprint on climate change. It also reminds us that Earth does not exist in a vacuum. We are part of a dynamic solar system, constantly bathed in a river of particles and magnetic fields from our star. This cosmic context enriches our environmental science, showing that to truly understand our home planet, we must sometimes look far beyond it, to the magnetic storms raging on the Sun that ultimately connect to the very air we breathe. If this journey into the heart of magnetic chaos has sparked your curiosity, the good news is that your exploration doesn't have to end here. Some of the most powerful tools for discovery are right at your fingertips, many of them completely free. A fantastic and dynamic starting point is NASA, a dedicated space weather website. This isn't just a static page, it's a live portal to our Sun. You can watch real-time data streaming in from satellites like the Solar Dynamics Observatory, seeing high-definition videos of solar flares as they happen, track sunspot numbers, and even get forecasts for auroral activity that might be visible from your backyard. It turns abstract concepts into tangible, observable events, allowing you to follow the daily drama of our star's magnetic life. For a deeper dive into the data itself, the community-driven platform HelioViewer allows you to become a virtual solar physicist. letting you layer different wavelengths of light from multiple solar telescopes to create your own custom images and animations of the sun's turbulent surface. For those who prefer the structured depth of a good book, there are some truly captivating reads that bridge the gap between accessible science and scholarly detail. Cosmic Magnetic Fields by Philip P. Kronberg is a respected and comprehensive work that explores the detection and influence of magnetic fields across the galaxy and beyond, perfect for the reader who wants to understand the evidence behind the theories. If you're fascinated by the human stories behind the science, Aurora, In Search of the Northern Lights by Dr. Melanie Windridge is a beautifully written travelogue that weaves together plasma physics, personal adventure, and cultural history as she journeys to see the lights. For a broader, yet still detailed, look at how magnetic fields shape the universe, The Magnetic Universe by J. B. Zerker provides a wonderful tour from the smallest particles to the largest galactic structures, all explained with clear prose and thoughtful examples. The world of online learning has also opened up incredible opportunities to learn directly from experts. Platforms like Coursera and edX offer university-level courses on plasma physics and astrophysics that you can audit for free. You might find a course from a leading institution that walks you through the mathematics of magnetohydrodynamics or offers a complete overview of space, weather, and its impacts on society. For more visual learners, the YouTube channels of NASA, Goddard, and the European Space Agency are treasure troves of expertly produced documentaries and animations that break down complex events like magnetic reconnection or the life cycle of a solar flare into clear, engaging visual stories. And don't underestimate the power of citizen science. Projects like Zooniverse often have initiatives where you can help professional astronomers by classifying sunspots or analyzing magnetic field data from real telescopes, turning your screen time into a genuine contribution to scientific discovery. These resources collectively empower you to move from being a passive observer to an active participant in one of science's most exciting and dynamic fields. At its core, the story of magnetic fields spiraling into light is far more than a physics lesson. It is a powerful narrative about the fundamental character of the universe itself. This process reveals a deep and recurring theme that echoes throughout nature: the profound and beautiful dialogue between chaos and creation. We often think of these two ideas as opposites, with chaos representing disorder and destruction, while creation signifies order and birth. Yet, the cosmos consistently shows us that they are not adversaries but partners in an eternal dance. The most magnificent structures, from the spiral arms of galaxies to the intricate patterns of a snowflake, often arise from turbulent, unpredictable beginnings. A magnetic field stretched and strained to its breaking point doesn't just vanish into noise, it reorganizes, focusing its pent-up energy into a brilliant, structured outpouring of light. This transformation is a universal principle, a physical manifestation of how potential is unlocked not through calm stability, but through necessary upheaval. This concept resonates far beyond the boundaries of astrophysics, touching on ancient philosophical questions about the nature of reality. Many creation myths from cultures around the world begin not with perfect order, but with a formless void or a churning chaos, a tohu wabohu in Hebrew tradition, or the primordial soup of Greek cosmology. From this tumultuous starting point, a cosmos of stars, life, and laws emerges. The magnetic universe offers a scientific parallel to these metaphysical ideas. It provides a tangible, observable process where we can witness the same principle in action. That dynamism, not stasis, is the engine of the universe. The cosmos is not a static painting but a living, breathing, and often violent performance, and it is within that very performance that beauty and structure are continuously born. This perspective invites a shift in how we view instability and turmoil, both in the cosmos and in our own lives. We are naturally drawn to equilibrium, to calm and predictable patterns. But the physics of magnetic reconnection teaches us that the most explosive growth and the most radiant transformations often occur at the edge of stability, at the precipice of chaos. It is when the system is pushed to its limits that it finds a new way to be, releasing energy and creating light in the process. This isn't a metaphor, it's a physical law. It suggests that the universe has a built-in preference for complexity and emergence, favoring systems that are dynamic and capable of radical change over those that are perfectly still. The chaos is not an error to be corrected. It is the raw material from which new order is forged. Ultimately, this journey through magnetic storms and cosmic light connects us to something deeply human, our innate desire to find meaning and pattern in the whirlwind of existence. For centuries, we looked at the unpredictable fury of a thunderstorm or the terrifying beauty of an aurora and saw the hand of capricious gods. Today, we look at the same events and see the elegant, albeit complex, workings of physical law. Yet, the wonder remains. Understanding the mechanics doesn't strip away the majesty. It adds a new layer of profound respect for the intricate processes that govern everything from the farthest quasar to the spark of thought in our own minds. We are not just observers of this dance between chaos and creation. We are products of it, living in a universe that seems fundamentally wired to turn turmoil into light. Behind every major discovery about magnetic fields and cosmic light, there are people, scientists and engineers whose passion and perseverance turn abstract equations into tangible truths. Their stories add a deeply human dimension to the science, reminding us that unraveling the universe's mysteries is a journey filled with challenges, eureka moments, and profound personal dedication. Take, for instance, Dr. Sandra Kaufman, who served as the Deputy Project Manager for NASA's MAVEN mission. Her journey to studying the magnetic environment of Mars began not in a university, but in a childhood of significant hardship in Costa Rica, where she and her mother sometimes lived in fear, taking shelter under a bed during thunderstorms. It was watching the Apollo moon landings on a small black and white television that first ignited her dream of working in space science, a dream that seemed almost impossibly distant at the time. Her path was not direct. She worked multiple jobs to put herself through college, first earning a 2-year degree in electrical engineering before eventually completing her studies in physics and electrical engineering. That long, determined journey culminated in her playing a pivotal role in a mission that would revolutionize our understanding of the Red Planet. The MAVEN spacecraft, short for Mars Atmosphere and Volatile Evolution, was designed to answer a haunting question. How did Mars, a world once warm and wet enough to have rivers and lakes, become the cold, dry desert it is today? A key part of the answer lies in the planet's magnetic history. Unlike Earth, Mars lacks a global magnetic field today. Billions of years ago, however, it likely had one, generated by a dynamo in its core. When that dynamo shut down, the planet's protective shield vanished, allowing the solar wind to steadily strip away its atmosphere over eons. MAVEN's job was to measure the current rate of this atmospheric loss and work backwards to understand the past. But the magnetic story on Mars is far more complex and patchwork than anyone anticipated, and it was Dr. Kaufman's team that had to navigate the immense technical and analytical challenges of mapping this invisible, fragmented landscape from orbit. One of the mission's most thrilling discoveries was the detection of unexpected and widespread magnetic anomalies locked within the Martian crust. These are remnants of that ancient global field, frozen into the rock like fossilized compass needles when the rocks cooled from lava millions of years ago. As MAVEN skimmed through the thin upper atmosphere, Its sensitive magnetometers mapped these invisible structures, revealing a bizarre and ghostly magnetic tapestry. In some regions, the crustal fields are strong enough to punch out into space, creating miniature, localized magnetic umbrellas that can actually deflect the solar wind and protect the atmosphere directly below them. In other areas, the fields are weak or absent, leaving the atmosphere fully exposed. This creates a bizarre patchwork quilt of protection and erosion across the planet, a stunning finding that no one had predicted with such clarity. For the scientists on the team, seeing this data for the first time was a moment of pure revelation. It was like finally being able to see the invisible bones of the planet's history. The human drama of such a discovery involves far more than a single eureka moment. It is a years-long saga of anxiety, focus, and triumphant collaboration. Dr. Kaufman has spoken openly about the intense pressure of the mission's arrival at Mars, the 6 minutes of terror during the orbital insertion maneuver where the entire team waited in breathless silence for the signal confirming the spacecraft had been captured successfully. That pressure then shifted to the long, meticulous process of data collection and interpretation, requiring immense patience and a willingness to be surprised. These personal narratives of working through the night, of debating the meaning of a strange data spike, of the collective gasp in a mission control room when a new plot appears on a screen, transform the cold, hard data into a story of human achievement. They show us that science is not a sterile, automated process. It is a deeply human endeavor driven by curiosity, camaraderie, and an unwavering determination to understand. Hearing Dr. Kaufman reflect on her journey from a young girl in Costa Rica to leading a team at NASA makes the science of Martian magnetism feel immediate and inspirational, a testament to how far curiosity can carry us. You don't need a particle accelerator or a multi-million-dollar space telescope to witness the invisible hand of magnetism at work. Some of its most fundamental principles can be explored with simple, safe, and truly captivating experiments you can do right in your own home. Let's start with one of the most classic and visually stunning demonstrations, mapping magnetic fields with iron filings. All you need is a strong magnet. A simple refrigerator magnet will work, but a neodymium magnet from a hardware store is even better. A piece of stiff paper or a thin plastic sheet, and a small handful of iron filings, which you can easily find online or at a science education store. Place the magnet on a flat surface, lay the paper on top of it, and then gently sprinkle the iron filings over the paper. Tap the surface lightly and watch in real time as the invisible becomes visible. Those tiny, dust-like fragments are each themselves turned into tiny magnets by the field, and they will instantly align themselves along the magnetic field lines, tracing out beautiful, looping arcs from one pole of the magnet to the other. You'll see the field concentrate at the poles, creating dense, brush-like patterns, and spread out into graceful curves in between. This simple act makes the abstract concept of a magnetic field into something you can literally see and touch, a direct window into the forces that shape the cosmos. For a demonstration that feels like holding a piece of the aurora in the palm of your hand, a plasma globe is a truly magical device. These captivating spheres, often found as novelty lights, contain a mixture of noble gases at very low pressure and a central electrode charged with high-voltage, high-frequency electricity. When you turn it on and place your finger on the glass, you become part of the circuit. The electric field from the center focuses through your touch, and the gas in that path ionizes, creating a brilliant, tendril-like filament of plasma. Now bring a small magnet close to the glass. Watch what happens to those ethereal beams of light. The magnetic field will interact with the electrically charged plasma, causing the filaments to bend, twist, and swarm towards the magnet. You are literally using a magnetic field to manipulate and shape a miniature star, a stunning demonstration of how these forces can guide and contort ionized matter. It's a safe, mesmerizing replication of the same principles that channel the solar wind into Earth's polar regions to create the northern lights. If you want to take the next step and actually create your own magnetic field, a simple electromagnet, it is a perfect and powerful project. Gather a large iron nail, about a meter of insulated copper wire, a D-cell battery, and some small metal paper clips. Wrap the copper wire tightly around the nail, leaving a few inches of wire free at each end. Strip the insulation from the ends of the wire and carefully connect them to the terminals of the battery. Immediately, that ordinary nail will become a powerful magnet, able to pick up a chain of paper clips. What you've built is a model of the very dynamo that generates Earth's magnetic field. An electric current moving through a coiled conductor, creating a magnetic field in the core material. The moment you disconnect the wire, the magnetic effect vanishes, proving the direct, intimate link between electricity and magnetism that James Clerk Maxwell described. This experiment is the heart of countless technologies, from the motors in electric cars to the giant magnets in MRI machines. And building it yourself connects you directly to that revolutionary discovery. These activities are more than just fun diversions. They are a powerful form of active learning. By physically engaging with these principles, you move the knowledge from an abstract idea in your mind to a tangible experience you can feel and see. This process builds a much deeper, more intuitive understanding than simply reading or hearing about it. It's the difference between looking at a map of a city and actually walking its streets. You gain a context and a connection that simply can't be replicated any other way. Whether you're doing these experiments alone, with friends, or as a family activity, they transform complex astrophysics into a personal adventure, making you an active participant in the thrilling story of how our magnetic universe works. While the dance of magnetic fields across the cosmos is a spectacle of pure science, its rhythms have a very real and powerful beat here on Earth, directly influencing our wallets, our jobs, and our global economic stability. This isn't just abstract knowledge, it's a critical investment that pays dividends across countless industries, protecting the infrastructure of our modern world and seeding the technologies of tomorrow. Every time a solar flare erupts, it's a stark reminder that we are a technological civilization living within the atmosphere of an active star, and understanding that relationship is no longer a luxury, it's an economic imperative. Consider the sheer scale of what's at stake. Our planet is now wrapped in a delicate web of satellites that provide everything from global positioning and weather forecasting to international banking transactions and live television broadcasts. A single, powerful coronal mass ejection, if it hits Earth directly, has the potential to induce massive electrical currents in our power grids, potentially frying multi-ton transformers that can take over a year to build and replace. The cost of such an event isn't just the price of the hardware, it's the cascading failure of a blackout that could affect millions of people for weeks or even months, crippling transportation, halting commerce, and threatening public health. By investing in the science of solar magnetism and space weather forecasting, we are essentially taking out an insurance policy on our entire way of life. Improved models that give us even a few extra hours of warning can allow grid operators to safely power down systems, put satellites into a protective safe mode, and reroute air traffic away from polar routes where radiation exposure spikes. The economic benefit of avoiding just one catastrophic event like the 1859 Carrington event in the modern era would be measured in trillions of dollars, completely dwarfing the entire budget of the world's space agencies. But the economic impact of magnetic research is far more than just defensive. It's profoundly innovative. The most ambitious example is the pursuit of nuclear fusion energy. The entire design of a tokamak or stellarator reactor is an exercise in applied magnetic physics, a direct attempt to recreate a stable piece of a star's interior here on Earth. The primary obstacle to achieving sustained fusion has always been controlling the plasma, preventing the very same kinds of magnetic instabilities we see on the Sun from instantly quenching the reaction. Every breakthrough in understanding how these kink instabilities or tearing modes work in astrophysical plasmas directly informs the engineers designing the next generation of fusion reactors. Success here wouldn't just be a scientific victory, it would be the ultimate economic game changer, unlocking a source of nearly limitless carbon-free baseload power. The global economic transformation sparked by cheap, abundant energy would be unprecedented, reshaping everything from manufacturing and transportation to agriculture and computing, while simultaneously addressing the immense costs associated with climate change. The ripple effects extend into nearly every corner of the technology sector. The miniaturization of magnetometers, driven by space science needs, is now in your smartphone, enabling the Compass app and sophisticated augmented reality experiences. Advances in superconducting magnets, developed for particle accelerators studying fundamental physics, are the cornerstone of medical MRI machines, a multi-billion-dollar industry that saves countless lives and reduces healthcare costs through non-invasive diagnosis. Even the development of more efficient electric motors and generators, which are fundamental to everything from electric vehicles to wind turbines, relies on a deep understanding of electromagnetic fields and how to optimize their force. This continuous cycle of pure research feeding applied innovation creates new markets, new companies, and new high-tech jobs, fostering economic growth that is both sustainable and transformative. This tangible connection between studying distant magnetic chaos and building a more prosperous, resilient society here at home makes the case that funding this science is not an expense, but one of the smartest investments we can possibly make. Perhaps one of the most inspiring aspects of our quest to understand magnetic fields is how it has consistently transcended national borders, uniting humanity in a shared scientific endeavor. The challenges we face are simply too vast, too complex, and too expensive for any single nation to tackle alone. This reality has forged a new model of discovery, where global partnerships and international cooperation are not just beneficial, they are essential. These collaborations represent a profound commitment to shared knowledge, proving that our collective curiosity can be a powerful force for unity and progress on a planet that often feels divided. A perfect embodiment of this spirit is the ITER project, an unprecedented international experiment currently taking shape in the south of France. ITER, which means the way in Latin, is a mammoth tokamak fusion reactor designed to prove the feasibility of fusion power on a commercial scale. But it is so much more than a machine. It is a diplomatic and logistical marvel. The project is a joint effort of 35 nations, including the entire European Union, the United States, Russia, China, India, Japan, and South Korea. These are countries with vastly different political systems, economic priorities, and historical relationships, yet they have all agreed to pool their financial resources, their brightest scientific minds, and their most advanced engineering capabilities to achieve a common goal. The components for ITER are manufactured in factories on every continent and then shipped to France for assembly, a global supply chain dedicated not to commerce but to the peaceful pursuit of knowledge. This intricate dance of coordination, where a superconducting coil might be built in Japan, a central solenoid in the United States, and vacuum vessel sections in Korea and Europe, demonstrates a level of trust and cooperation that is as groundbreaking as the science itself. The drive to understand space weather has sparked its own web of international alliances. No single country can monitor the entire Sun or the full scope of Earth's magnetosphere from one vantage point. In response, space agencies have created a distributed network of observatories. NASA's Parker Solar Probe flies closer to the Sun than any spacecraft before it, while the European Space Agency's Solar Orbiter provides unique high-latitude views of the Sun's poles. Meanwhile, a fleet of satellites from various nations, including Japan's Hinode and the joint ESA/NASA SOHO mission, constantly monitors solar activity from different orbital perspectives. The data from all these missions is shared openly and rapidly across the global scientific community. When a solar storm erupts, researchers from dozens of countries immediately begin analyzing the same datasets, working together to model the storm's path and predict its impact on Earth's technology. This isn't a competition. It's a global relay race where the baton of data is passed freely to ensure everyone crosses the finish line together, better prepared and more knowledgeable. This collaborative model extends far beyond our solar system to the most ambitious astronomical project in human history, the Event Horizon Telescope. Capturing the first ever image of a black hole required synchronizing a global network of radio telescopes across 8 different observatories, from the high deserts of Chile to the volcanoes of Hawaii and the frozen peaks of the South Pole. To achieve this, scientists had to combine their signals to create a virtual telescope the size of Earth itself. The effort required flawless coordination across international time zones, cultures, and scientific traditions. The resulting image, a glowing ring of light around the supermassive black hole in galaxy M87, was not a victory for one institution or nation, but a triumph for all of humanity. It was a vivid reminder that the universe does not recognize our maps and borders. Its mysteries are a common inheritance, and they are best solved by looking outward together. These partnerships do more than just advance science. They build enduring bridges of diplomacy and friendship. In the clean rooms and control centers of these international projects, engineers and scientists from around the world work side by side, sharing meals, ideas, and a common purpose. They build personal relationships that often survive political tensions between their home countries. This creates a resilient layer of people-to-people connection that operates outside of government politics, fostering a spirit of goodwill and mutual respect that can have a stabilizing effect on international relations. By uniting around the peaceful exploration of fundamental forces, these collaborations demonstrate that our shared humanity and our common desire to understand the cosmos can be a more powerful narrative than division. This remarkable chapter of global teamwork provides the perfect foundation for the final thoughts we will share as we bring our exploration to a close. And so we reach the end of our journey, a voyage that began with the simple pull of a magnet and carried us across the cosmos to the edge of black holes and the birth of galaxies. We've witnessed the incredible story of how invisible magnetic fields, when stretched and strained to their absolute limit, can spiral into magnificent chaos and in that very act of unraveling, become the universe's ultimate artists sculpting jets of matter, painting the polar skies with shimmering light, and igniting the most violent explosions since creation itself. From the solar flares that leap from our sun's surface to the hypnotic pulses of distant neutron stars, we've seen that this process is a fundamental rhythm of the cosmos, a constant dance between order and chaos where destruction and creation are two sides of the same brilliant coin. What's truly remarkable is how this story connects the vast and distant to the intimate and personal. The same forces that carve out the structure of a galaxy millions of light years away are the very ones that guide a sea turtle to its nesting beach or allow a doctor to see inside the human body without a single incision. It's a powerful reminder that we are not separate from the universe. We are a part of it, living within its laws and shaped by its forces. The aurora dancing over your head isn't just a pretty light show. It's a direct message, a cosmic postcard sent from our sun and delivered by Earth's magnetic embrace. Understanding this deep connection transforms the way we see the night sky. It's no longer a static painting but a dynamic, living performance, and we have a front row seat. This isn't just a story for scientists in labs. It's an invitation for all of us to become active participants in the wonder of discovery. Your engagement with this mystery doesn't have to end when this video does. You can step outside on a clear, dark night and simply look up, knowing that the stars you see are shining because of the very processes we've explored. You can chase the aurora, armed with nothing more than a weather app and a warm jacket, and feel the thrill of witnessing cosmic forces at play. You can dive into the incredible resources available online, from NASA, live solar data to citizen science projects that let you help classify sunspots from your laptop. Every question you ask, every photo you take, every new fact you learn deepens your own connection to this grand, unfolding story. The greatest takeaway is that the universe is not a cold, empty void but a place of immense dynamism and breathtaking beauty, where even chaos has a purpose and a pattern. The magnetic fields that spiral out of control do more than just create light. They create understanding. They challenge us to be curious, to be collaborative, and to look beyond our own world with a sense of wonder and responsibility. So the next time you feel the pull of a simple magnet or glimpse a news report about a solar storm, remember the incredible journey behind it, a journey of invisible forces, chaotic beauty, and the enduring human spirit that strives to make sense of it all. Thank you for joining me on this exploration. If you've enjoyed unraveling this cosmic mystery with me, be sure to subscribe and hit the bell so you don't miss our next adventure into the wonders of space. I'd love to hear which magnetic phenomenon captured your imagination the most. Was it the raw power of a solar flare, the elegant dance of the aurora, or the precise clockwork of a pulsar?